Yeah, it's a great question. So the question is, tracing is difficult in tree recursion problems. So how are you meant to think about them? Is there some way to trace through how they are evaluated, or some trick to thinking about whether you're on the right track? And tracing is not your friend. So tracing means actually kind of writing down each call or building out the environment diagram, kind of describing every step in the process to evaluating a function. And yeah, for tree recursion problems, it's really not very useful. Sometimes tracing helps for the first two calls that you make from the kind of original call, just to make sure that you're passing the right arguments in. But then if you're going to continue tracing, all of a sudden you're going to make two more calls and two more calls after that. You build this tree structure. Does it make sense to draw out the tree? I would say almost never. Instead, the skill you're trying to build at this point is to not worry about how the recursive call works, but instead assume that it behaves as it's supposed to behave, and therefore skip all the parts between when you make the recursive call and when it returns. The mechanics of that don't really matter. What matters is you called your recursive function, you got something back. You should know what it gets back based on how the recursive function you're implementing is supposed to work. So if it's supposed to, count the partitions of something, you're supposed to get that count back. And you can think about what that count is without tracing through the code. Then the tracing can return again as you make sure that your original call returns the right things. So I would say trace everything that's happening in the body of the function until you get to the recursive call itself. You don't want to trace through what's happening there. Instead, you want to just assume that it works and kind of replace that recursive call with its return value, and then continue tracing from there. So I think there is a case where some sort of partial tracing is very helpful, and that's to figure out what your base cases are supposed to return and to make sure that you always hit a base case, regardless of what argument you pass in the first place. So let's talk about the count partitions function from lecture. I think it's very natural to ask, like, oh, if I pass in 12 originally, like, well, you're supposed to pass in two numbers, m and n, but let's just say like we pass in n is 12. Am I ever going to hit either of these base cases? That involves a certain kind of tracing where you don't consider the whole tree. You just consider like paths through the tree. Or you say to yourself like, oh, if I pass in n is 12 and m is 5, so that means I'm going to subtract 5 from 12. Like, I know I'm going to get to a case where n is now 7. And I know that after that, I'm going to get to a case where the n is now 2. And then after that, I'm going to get to a case where n is now 2 minus 5 is -3. Do I have a base case for that? So in that sense, I am sort of looking into the future of what's going to happen as I recursively evaluate this function and asking myself, what arguments will my recursive function be called on in the future during evaluation based on the original call? And along all those chains of calls, am I sure that I'll always hit a base case? Because it's very important that you always hit a base case, otherwise it will just run forever. So here, you don't necessarily want to think of every recursive call that's made and all the branching. You just want to think about the patterns that emerge. So like you start at 12 and you're going to subtract 5, you get to 7, you subtract 5 again, you get to 2, subtract 5 again, you get to -3. Like, do I handle negative numbers in my base case? If so, how should I handle them? You can look at one previous call from the base case. So you can ask the question, if I am counting the partitions of 2 using parts of to size 5, I know I'm going to hit this -3 base case. Like, what does that mean in this context? I think it means in that context that there's no way to make the number 2 out of a 5 and something else, because something else would have to be -3, and you're not supposed to be using negative numbers. So in that sense, you can come up with an interpretation for the base case, which is that when you hit a negative n, there's no way to partition it, so you return 0. And you can kind of check in the body of the code that returning 0 makes sense, because you're going to add this number to something else, And the something else that you added 2 is supposed to give you all the way. So actually partitioning 2 using numbers that work, not numbers that are too big, like 5. So yeah, I said don't do tracing, but there is some amount of, like, to check this thing works, you do want to make sure that you're going to hit base case. And that means thinking about what arguments will be passed in the future. Again, I'm not really looking at the body of the function and tracing through every assignment statement and every if. I'm just asking myself, based on the recursive pattern I've set up, like, what arguments will come in to the recursive function based on the original, and will they always hit a base case? And if so, are my base cases returning sensible values in all cases? Yeah, so this was an example from the tree recursion lecture. We can look at the original call, which has n and m, and they're supposed to be positive numbers. Like, that was sort of laid out in the problem description. Then when I think about tracing to make sure I hit the base cases, I really just have to look at the recursive calls themselves. Like, not worry so much about the details of what's happening here or how things get added together, but just ask myself, what kinds of arguments are going to be passed into count partitions? If I started with 6 and 4, then I'm going to get 2 and 4. Now that I get 2 and 4, I'm going to get -2 and 4. So I have to make sure that I handle negative values in some base case. Otherwise, from -2, I'll get to -6, I'll get to -10, and it'll just go forever. What happens in this recursive call is that n stays the same, but m decreases by 1. So if I start with m as 4, then I'll get a call 6-3, and then I'll count a call 6-2, and then 6-1, and then 6-0. So I better have a case where m is 0 in my base cases. Here it is. So I'm covered. How come there's no negative m here? Well, if m is just starting at a positive number and working its way down by 1, then it's going to hit 0 before it ever goes negative. So these were the two recursive calls I was talking about, and how to kind of trace them without going through every detail of what happens, what values do they return. You just want to know which recursive calls you're going to make in order to get the right base cases. So I'm supposed to get some notion of how many ways you can divide up -2 using parts up to size 4. Like, that's kind of counterintuitive, dividing up a negative number.
Yeah.
So why would I return 0 instead of 12 or an empty list or something like that? Well, I'm going to add this, whatever it is, I'm going to add it to something else. So better be a number. And this is talking about using a 4 to make up the number 2. But you can't fit 4 into 2. So in that sense, like, this case, this branch of using the number 4 to get to 2 should be 0, because there's no way to use a 4 to add up to the number 2 if you're only adding together positive numbers. So you'd think, oh, with this case should work out to, there's 2 ways to make 2, 2 and 1 plus 1. So this is your 2 and this is your 0, and that's how you count the partitions of 2 using parts up to size 4. So yeah, that level of tracing I think is helpful for understanding why the base case return value is what it is that you go one step before the base case and ask yourself, what values do I need in order to get the right result for one step before the base case? Because I know I'm going to hit the base case here, and I want to make sure I get the right value here in order to finish this off. Right. If for anyone whose reaction is, like, these base cases are weird, I thought I was like handling positive numbers, and now I'm hitting zeros and negatives. Like, what is going on there? The base cases are set up to make sure that this return value is correct when you get positive n and m in. So you have to think about, for positive n and m, which are about to hit the base case, what value do I want to get back? Is one way to think about these base cases. Okay, great. Yeah, great question. So the question is, how does count partitions actually keep track of the intermediate counts that you need in order to compute the right value at the end? At the end, you're going to compute this 9 out of 2 components. The ways of getting 6 if you use a 4. I think there aren't too many of those. There's 4 plus 2, and there's 4 plus 1 plus 1. Those are the only ways to get 6 if you're using a 4. So there's 2 of these. And then it turns out there's 7 of these. And I won't list them all out, but they're things like, 3 plus 2 plus 1, etc. And then you add together the 2 and the 7, and you're done. But this 7 was made up of other numbers. So in particular, this was count partitions 6, 3. How did I get that? Well, I just look at n was 6 and m was 4, and we subtracted from 1 from 4. So we got 3. Okay, so there's 7 ways to do this. And when I call n and m on 6 and 3, I get another with m and without m. Except this time, the second time through, m is 3. And so I get a different answer here. And I get a different answer here because I'm computing different things. And then I sum them up and they get returned. So how is it that Python kind of keeps track of all these and somehow comes up with the number 9 or the number 42 when this thing only ever returns 1 or 0 or 0 or some like mysterious thing that involves computing recursive calls? One thing to keep in mind is that this number 9 is just a sum of a bunch of different base cases. So a bunch of different 1s and 0s at the end of the day. And I don't know how many 0s there were, but I'm pretty sure there were 9 1s because it got up to 9. So in all of the recursive calls that were made for count partitions 6, 4, 9 of them were a base case where n equaled 0. I don't know which 9 they were, and I'd rather not care. That's like something for computers to figure out. But it is the case that when you run one of these things, what you get at the end of the day, if all you're doing is adding in the recursive case, is some sum over the base cases. So somehow we added 9 different 1s together. How did Python keep track of that, and when did it happen? Here, I'd say it's a good idea to actually glance through Python tutor to see what's going on. So tutor.cs61a.org, we're going to count partitions of 6, 4. We're going to close the frames when a function returns, just so things don't get too crazy. There are 393 steps, so we're definitely not going to draw the whole environment diagram here. But we are going to get a sense of how Python keeps track of these things. So the original call to n equals 6 and m equals 4 is in a frame, which makes a recursive call to 2, 4, there it is, which makes a recursive call to -2, 4. Okay. And then this actually hits a base case here, like right away. And so it like doesn't need to do any more work. But what's interesting here is that that now sets a value for with m within one of the frames that was created before. And that means an intermediate value is being stored within a frame, which is part of the computation. Not a very interesting part because it's still just 0, but it is the place in which intermediate values get stored. So it keeps making recursive calls for a while. And eventually this call here is going to return. Now let's see what happens when that happens. Okay, so it just returned here. And where it returns is that it sets the with m value within the original call to count partitions. So that 2 is stored just long enough to add it to, we'll eventually get 7. So if we go all the way to the end, we'll get the 7 that we added to, and that makes 9. Now, where did the 7 come from? This 7 actually came from the recursive call to 6, 3, which used some 3s or didn't use some 3s. So what does it mean to use a 3? That's like 3 plus 3, or 3 plus 2 plus 1. And without a 3, that's like a 2 plus 2 plus 2. All the ways to make 6, this return value of 7 was built out of a 3 and a 4, where actually the 3 was around for a long time, stored right here, waiting for the 4 to add it to. And finally got around to finding that 4, adding them together. Now this 2 that was stored long ago the ways of partitioning 2 using parts up to size 4 is finally ready to be added to the ways of partitioning 6 with parts up to size 3 in order to get the return value of 9. So that's how Python stores it, is in different frames. You have a bunch of different with m's and without m's. You don't want to think about it that way, or you'll go crazy because you can't go through 393 steps in your head. Instead, you want to think about it as count partitions finds the ways of partitioning the number 2. Count partitions here finds the ways of partitioning all 6 using smaller parts only up to size 3, but no 4s allowed. And so I get 2 of them this way and 7 of them this way, and that's how I get 9. A student joined the office hours session and asked a similar question as was asked before about the base cases of count partitions, which was great because then I got a second chance to try to explain it. So if this seems redundant, it's pretty similar to the question that was already asked, but I try to answer it in a slightly different way. Hope it worked. So the question is, how do you come up with the base cases for a problem like count partitions, or count partitions in particular? Yeah, let's talk about that for a second. So count partitions is supposed to be about positive numbers, and all the base cases are about zeros and negatives, which is weird. But it happens to be that there are like lots of different ways to reach negative numbers and lots of different ways to reach m equals 0. But what we want are base cases where when you make recursive calls that hit a base case, you get values that help you compute the right result. So what should the base cases be? Like, what are you looking for? Well, there you have to think about all the different recursive calls you might make and make sure that you handle all the cases that are kind of should be simple to handle. What should they return is they should return values that you've just hit a base case. You now have a return value from a base case. Is it the right return value to compute the correct result at the end? So for 6 and 4, you're not going to hit a base case either way here. But let's try something else. Like, let's pretend we're count partitions 2 with parts up to size 3. How do you partition 2? Well, it's either 2 or it's 1 plus 1. Neither of these involve a 3. But if I look at my code, I'm going to make a count partitions call on something comma 3 right here. What's the something? Well, it's 2 minus 3 is negative 1.
Minus 1.
How many ways can you make 2 using a 3 somewhere? Well, there aren't any. None of these use 3s. So this should be 0. That should contribute 0 to the sum. The sum should be from these, right? Which are the ways of count partitions 2 comma 2. There's 2 of these. Okay, so that kind of helped me set this 0. Is I saw that n was less than 0 and the value that I wanted was 0. Okay, so now we consider 2, 2, which has the same result. Counting partitions of size 2 using parts, counting partitions of 2 using parts up to size 2, when I use a 2, gets me to count partitions 0, comma 2. There is a way to make 2 using a 2, which is just 2. So there should be one way to do that.
Right.
Hence this return value. We came up with a way to detect cases like this, and we came up with a way to assign a value to them based on the goal of the function. The question is, like, how do you come up with this split in the first place between with m and without m?
Yeah.
That's actually the first step before all the base cases.
Right.
In this case, is you got to think of, I'm trying to do this thing, which is come up with all the ways of adding up to 6, using parts up to size 4. How do I describe that in terms of simpler versions of the same problem? And that is not a question that's obvious to answer. In fact, it's different for every tree recursive problem. How do you take the set of all things you're trying to count up, find a way to split them into 2 groups, such that you can count each of the 2 groups and you haven't double counted anything. That's what you're looking for. Now, I kind of told you what it was in this case. You didn't have to come up with it. I said the way we're going to count the two groups is we're going to define one group as things with a 4 in it, and another group which is things that have no 4 in it. I think that there aren't any duplicates in there, and then we can count both groups. Why can we count both groups? Well, because it happens to be that both of them are a call to count partitions. You count up all 6 using parts up to size 3, which means I never used a 4. Or I did use a 4. When I use a 4, I don't have 6 left. I only have 2 left because I've already used a 4. So then I count 2 with parts up to size 4. So that logic is kind of where you begin. Is you say, like, how am I going to take this problem and divide and conquer my way through it by doing the same operation over and over again with simpler instances of the problem. Once you've got that split, then you've got your recursive case. You figure out how to express it in code, which is also not trivial. Like, we had this notion that we were going to count up 2 groups, and then we were going to return the count of both groups together. Well, it turns out plus will do that for us. How do we describe each group? Well, I'd say this one is a little bit more straightforward. This says, like, I want to use parts that don't include 4, so I'll just use 3 and lower. So that's okay. I need to know what the second argument means. But other than that, like, I just subtract 1. And then what the heck is going on here? Well, this is the notion that we've already used up an m, which was 4. So we've already used up a 4. So what's left is we need to finish off the 6. So when I use a 4, then what's left is like only adds up to 2. So this is how we express it in code. Okay, now we have our recursive calls from our recursive idea. And then what we talked about for a while before was, how do you get your base cases right? There's 2 parts to that: figuring out what base cases to detect. So, like, what are the simple cases? And then what should they return? And for thinking about what they should return, it's best to think about cases where you're about to get to the base case. So one more call and you'd hit a base case. And make sure that you get the right values for with m and without m in order to handle that case well. So that's when we were talking about count partitions 2, is going to hit a base case where there's nothing left to count. We're down to 0. What should happen there is we should declare that, oh, we found exactly one way to partition the original n, which was 2, which is with a 2. But there's nothing left to add in. So there's not like a bunch of different alternatives to count. There's just 1, which is why we return 1. So all those parts have to go into solving a recursive problem like this. Figure out your strategy, figure out how to express your strategy, and then make sure that it ends in the simple cases. Yeah, this is a great question. So when we go back to the 6-4 case, what happens down here? We do 2-4. There are 2 ways to do this. I'll describe them in a minute. We also do 6-3. There are 7 ways to do this. I can describe some of them in a minute. But it's true that you do both. And then this 9 comes from adding this 2 and this 7 together. And neither of these are a base case. Both of these have to do a bunch of work, because this has to discover all the ways of summing up to 2, which is 2 and 1 plus 1. This has to come up with all the ways of summing up to 6, except I'm not allowed to use 4s anymore. So I have stuff like 3 plus 3. I have stuff like 3 plus 2 plus 1 in there. I also have stuff like 1 plus 1 plus 1 plus 1 plus 1. That looks like. So there's 7 of these. I only wrote out 3 of them, but you can guess some of the other ones. My point is that, like, if you went through and said, okay, now how do I solve 6,3? You'd end up with a headache and not much progress. You have to assume that 6,3 works already. That when you make your recursive call, you're going to get a 7. Just like, trust the system. When you make this recursive call, you're going to get a 2. You're going to get all the ways of adding up to 6 using parts up to size 3. And once you have those 7 ways counted, recursion does the work for you. And these 2 ways counted, recursion does the work for you. How do you get the whole list? Well, you've gotten all the ones where you use a 4. You've gotten all the ones where you don't use a 4. You add them together and you're done. That's the key. So the tendency is to ask, like, oh, how do I solve this problem given that I'm trying to solve 6,4? And the answer is, you don't solve this problem. You, in fact, already solved it. as long as you handle the 6-4 case and you do it in a way that's sufficiently general and you get all the base cases right, then you've also handled the 6-3 case and the 6-2 case and the 6-1 case and the 5-3 case and all those ones that you'll hit along the way. Let's look at this base case and how it corresponds to this recursive call.
Yeah.
In fact, this recursive call will never hit this base case.
Right.
Instead, this recursive call, if it hits a base case, will hit this one. And why does this make sense? Well, basically, we started at 6-4, we went here. Now we're at 6-3. If we go here again, we'll go to 6-2, then to 6-1, then to 6-0.
Right.
And when we get to 6-0, we're asking ourselves, how do we make a 6 using no numbers at all? Well, there aren't any ways to do that.
Right.
We're like out of
Option
options.
0.
Okay. But also, when we hit 6-3 here, within the 6-3 call, we're doing this branch as well.
Right.
So even though this never hits this base case, this will hit this, which hits this base case eventually. So there's lots of ways to get to this base case from here. It's just none of them are direct. But you do need to look at this call and say like, oh, what's going to happen to M? It's going to go down and eventually it's going to be 0. And so I need to have a solution to what happens when it gets to 0. And you have to reason about what that means. What happens when M is 0? It means you're not allowed to like use any numbers anymore. So there's no way to do it. Spend a while on this one. It's worth it. I know that it's not easy to get your head around. That's kind of the idea. And by the way, before I started teaching 61A, this problem was on the second day of class. So at least you've gotten like some way to work up to it. But it's always been part of the course and it's always been a big challenge. And it's one of those things that once you get it, it's going to feel good. But it takes quite a bit of practice just looking at this problem to understand it and then looking at how that applies to similar problems, which you'll have to do on your homework. And you will just get better at it if you spend time on it, but it's not something that ever comes quickly. Okay, so the question is, how does count coins on the homework relate to count partitions from lecture? They're almost the same problem, but the differences are important. So let's talk about a recursive strategy that will work here, and then talk about how the implementation would change in order to get it to work. So again, you're trying to figure out how to sum up to some total given parts, right? Except now you can't have a part of arbitrary size. Like in count partitions, when we were summing up to 6, we could add 3s in there, we could add 2s in there, we could do whatever we want. Here we have a restriction, which says we can only use parts that are one of the US coin values. So you can't make 6 by 2 plus 2 plus 2, because there's no tuppence in this problem. The only way to make 6 is 6 pennies or a nickel and a penny. That's like, so there's only 2 ways, right? And likewise, there would have been tons of ways of making 15 in count partitions, because you could either use some 7s or some 6s or whatever. But here there's only a few. Like you do 10 and 5, or you do 5 and 5 and 5, or you 10 and a bunch of pennies, etc. Like you can kind of work out the options, but there just aren't that many ways to do it. Okay, the structure of the solution isn't so different from count partitions. There are still some base cases. There's still an amount that you want to make change for. You could still have a notion of the biggest coin you're willing to use. And there's still a notion of, I use at least one of those. So if M is a nickel, I use at least one nickel. Or if M is, or I don't use any nickels, at which point I should be using only pennies. The way we transitioned in count partitions from a size of 4 to a size of 3 was by subtracting 1. Yeah, with subtraction. But the way we would transition from nickels to pennies is something different. It's like a call to give me the smaller coin. Okay? So this is going to change. Other than that, it's a pretty similar problem.
Right.
Now, there's one other piece, which is this takes 2 arguments, but this only takes 1. What do we do about that? What if we wanted to count all partitions of n? Count all. So this would be like count the partitions of n using parts of any positive size. How will we solve this problem? If we've done all this work to count partitions of n using parts up to size m, I'd sure hope we do it by calling count partitions of n using parts. Well, a part bigger than n is useless. A part smaller than n might leave something out. So what are we left with? N. If our goal is to get all the partitions, but the recursive strategy requires us to keep track of the kind of biggest part, then that's fine. Still implement it using the biggest part, but start with a really biggest part. It's a special feature of count partitions that if you're trying to partition 17, you can just use a 17. There's no 17 coin, right?
Right.
You're going to have to go do some work to find what's the biggest coin you might actually use. Or you could just start with the biggest coin there is. I mean, either way would probably work.